Okay, what about this one? So integrating this between 0 and 1, how do we go about doing that? It's not a standard integral, is it? Look at your table of standard integrals, it's not that. So what we need to do now, and it's going to be the same for all our techniques we're looking at today, the whole point of what we're going to do today is to get your integral to look like something on that standard integral sheet so that you can then do it. Well, this particular, not this one, but the next one will be. So yeah, this is just integration techniques would be a good general title, integration techniques. Okay? Before half term, I left you with a little exercise, I think, and that was to try using Maclaurin's series to write down the power series for one of the functions, the sine function or the cosine function. I can't remember which one I asked you to do now. Hopefully it was a sine function. I can use Maclaurin's series to work out what the power series is for the sine function. It's that. Make a note for yourselves, please, to use Maclaurin's series to prove that that's true. That the sine of theta, oops, made a mistake here, the sine of x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. That'll be a really useful exercise for you to do to check that you can use Maclaurin's series. It turns out that all the even powered factors disappear and we're only left with the odd ones. So that's the power series for the sine of x. Notice this, approximately given by. The more terms I add, the closer we get to our value of sine of x. And remember I said to you on the calculator, if I worked out what the sine of, say, 30 degrees was, or 1 radian as we've just done, it actually uses a power series to do it. So to get a value of sine of x on the calculator, it uses the power series form anyway. How can I use this to help me with this, to do this integral? I replace sine theta in here with the power series. So let's do that. So the integral becomes the integral between 0 and 1, so it's going to be a definite integral, of theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus theta to the 7 over 7 factorial over theta. Okay, so remember this, by the way, is found using Maclaurin's series, as I just mentioned a second ago, and that's when x equals it, when you're doing it around 0, the origin. Taylor series is when you're doing it around another point, say a. But if you remember, if a was 0, it's called the Maclaurin series. So we're using Maclaurin series to do that. In other words, so long as x is near to 0, then that's okay. Because if we were to plot the function of sine x and then plot the power series, do you remember it looked like the sine function, or it looked like the function we were after, so long as you're fairly close to where you've set this generated this power series. So how many of these terms do I include? Well, that depends on how far away from your 0 is. In this case, you're going to try and use it. And we're going between 0 and 1, so you might decide, okay, well, I'm going to add maybe another term. So it's an open question as to how many of these series you include. Yeah. Now, yes, good point. Okay. So what do? Now we can actually simplify this. If I've got a fraction with one number underneath the denominator and a whole series of numbers on top in the numerator, what can I do with that fraction? Split it, exactly right. I can write, this is the same as the theta over theta minus theta cubed over 3 factorial times theta. The theta goes underneath with the 3 factorial plus theta to the 5 over 5 factorial times theta minus theta to the 7 over 7 factorial times theta. And we could add more terms if we wanted to. We can split the fraction, exactly right. If there's only one number in the denominator, we can do that. Well, actually, we can do it with more than one, but we'd have to use the whole denominator. We can't split it up. Now what can we do? We can do some cancelling. We can simplify each term, can't we? I can cancel these thetas, and what am I left with? 1, right, okay, not 0, 1. Theta goes into theta 1, theta goes into theta 1, so that will be replaced with 1, and I can do some cancelling here. That becomes squared, this becomes to the power 4, and so on. So I can now write that the integral becomes 1 minus theta squared over 3 factorial plus theta to the 4 over 5 factorial minus theta to the 6 over 7 factorial, and so on. Now, if you look at your table of standard integrals, we've actually got that on there. We can integrate each of these terms separately when we integrate, and so I can now use one of the standard integrals. I can use this one, the top one on this table here. So what do? I add 1 to the power and divide by the new power, if you remember. And because it's a definite integral, we're not going to worry about the standard of integrals. So for each of those terms in there, I'm going to add 1 to the power and divide by the new power. So I'll just pause for a sec while you do that, and then put the limits in. If you go as far as this term here, so you're going to have 5 terms that you're going to integrate. What happens with this one, by the way? What does 1 become when you integrate it? Sorry? Exactly, so 1 theta in this case, so it just becomes theta. Yeah. So I'll just pause this for a sec while you have a go at it. So we'd end up with this, and then we could put our limits in, as we did before, the 1 and the 0. The 0 is going to be quite easy because all the terms will disappear. So effectively, you're just going to have the 1, aren't you? So it actually becomes 1 minus 1 over 3 times 3 factorial plus 1 over 5 times 5 factorial, 1 over 7 times 7 factorial. And then I just get my calculator out and work out what that was. And that would be the answer. It would be an approximate answer because we've used the power series, and the more terms we have, the better our answer will be. Okay, let's go back to this. What happens, what would it be if it was sine theta over theta squared? Could I use the same method to do it? Why not? Couldn't I? I'd just be dividing by theta squared each term, wouldn't I? And then I could simplify. Exactly the same idea. Could I do it if it was the square root of theta? Yeah, theta to the half, and again I could do cancelling. Okay. Would it work if instead of being divided by theta, I times by theta? Could I use the same technique then? Think about our power series. Yes, that's right. Here's the power series. So instead of that being divide by theta, it was times by theta. I could do exactly the same thing, couldn't I? I just times each one by x. So this would become theta squared minus theta to the 4 over 3 factorial, and so on. I could use exactly the same idea, couldn't I? So, and if it was a different function, remember we can write most functions as power series. So this is a very common technique in integration. If you're stuck of how to do the integral, you can use Maclaurin or Taylor's series to work out what the power series is and then integrate that. Because you're reducing it to a whole series of terms, and then we just got to use that top standard integral on here, this one. Job done. Okay. One disadvantage is, of course, that it's an approximate answer. And the more terms you add, the better it gets. So we're going to look now at some ways of actually coming up with exact answers.